Hi, my name is Hope Kaminski, and I will be talking about my research and investigation into carbene intermediates through the synthesis of sulfonium Ylide precursors. Carbene intermediates are carbon molecules with one lone pair of electrons and two bonds, as opposed to a full octet. The molecule does not have the four bonds typically observed for stable carbon species. In Figure 1, notice the paired versus unpaired electrons in the singlet and triplet states. They show different reactivity due to their different electronic configurations. Because of their lack of a full octet, carbenes are highly unstable. Because of this, carbenes do not last long unreacted in normal conditions on Earth, but the molecules tend to be found in abundance in interstellar space, where the freezing temperatures and vacuum keep the molecule stable. Carbene intermediates have particular use as the transition state molecule in reactions, helping create new carbon-carbon bonds via metal-catalyzed reactions, as illustrated by this generic depiction of a metal-bound carbene. The carbon-carbon bond forming characteristic of carbenes is particularly useful in pharmaceuticals and in the synthesis of polymers and plastics. However, carbenes are difficult to isolate outside of low temperature and pressure systems. Due to their instability, a stable precursor is synthesized. Tosyl chloride and sodium azide are combined to make tosyl azide that is reacted with a malonate derivative here. The hydrogens on the central carbon of the malonate derivative are replaced with a double bond to nitrogen to generate the diazo compound. A transition metal catalyst is then used to facilitate the addition of thiophene to the readily accessible central carbon on the diazo compound. The sulfonium Ylide provides a comprehensive route to forming carbene intermediates. Irradiation breaks the carbon-sulfur bond, the thiophene acts as a leaving group, and the carbene intermediate is generated. Figure 2 is of the diisopropyl diazomalonate infrared spectrum. Infrared spectroscopy utilizes the vibration characteristics of bonds to tell us about the functional groups on a molecule. A small sample is placed on a crystal, and infrared light is shown through the crystal and the sample. This vibrates the bonds of the molecule. Different bonds and bond lengths vibrate at different frequencies. That information is transformed into the spectrum you see here. The added diazo group, which is combined of the two nitrogen atoms double bonded to each other, gives a characteristic strong stretching frequency around 2200 inverse centimeters, which can be seen here marked with a star. This indicates success of the reaction. Figure 3 is of the attempted diisopropyl sulfonium Ylide synthesis. This synthesis was attempted 2 times. The first did not seem to yield desired product, while the second attempt, showing the lack of the diazo stretch, indicates the starting material for the reaction has been consumed. This is very promising. Now that diisopropyl diazomalonate precursors have been synthesized, work is being done to optimize conditions for the sulfonium Ylide. Future work on the sulfonium Ylide will then be done to produce the carbene intermediate once the sulfonium is successfully synthesized and purified. This involves irradiation of the sulfonium Ylide with light in the presence of a trapping agent and allows for the formation of stable products that can then be analyzed. I would like to thank Dr. Farr for her many hours of guidance and years of research into carbene intermediates and organometallics. Thank you for listening.